Hello, hello. Okay, for this video, I'm going to run through the R code that you'll be using to run your first ANOVA and for the lab for this week. So first, we'll start off with our importing our data set. We're going to import it by making this object that we're going to call CH15DS1. We could call it Pink Flamingo, Flying Spaghetti Monster, whatever we want, but we're going to call it something that makes sense just to keep it easy on ourselves. So to download the data file, we can go to the course page. And if you click on, the week 14 page, then you have your practice data file. Cool. Okay, so you download it. I already downloaded it once, but you'll download it. And then when you run your code, you can find it where you downloaded it. So if you didn't move it, it'll be in your downloads. So I just search for the name, open that puppy up. Okay. You can click on it and just get a look at your your data set. You can see here that we have two variables, essentially, or two columns. One is describing the group that people in our data set belong to. So this is preschool, a preschool sample, and it's kids who are in these kind of language learning programs, it sounds like, according to your book. So some kids were in a 5-hour program, some were in a 10-hour program, and then some were in a 20-hour program. And then that is you only see those three differences. So that's our grouping variable, and then we want to know ultimately how much these language scores vary. So, how much these language scores vary based on group. So let's say, we gave each kid in our sample a test and they could score anywhere between 0 and 100 on this language test. We want to know if these programs that they're in are helping them increase their language scores. Okay, so that's just looking at the data set. Now we can run some descriptives to get a little bit more information about our different groups. So because we're running an ANOVA, we're looking at these three different groups. Maybe we just want to get a sense of how different these groups are, just in terms of general descriptive statistics. It's always good to do this sort of just broad overview of your data when you're doing a research project, because it allows you to see if there are any problems or any weird things, and just kind of get a general picture of what's going on. If, for instance, the language score should only be between a 0 and a 100, and you found one that's 500, maybe it's a typo. Maybe there's an error in there for some reason. So this step allows you to see these types of issues. So we're going to use this describe by function. And the describe by function is in the psych package. So you can see I've already kind of practiced the R code here, but let's go and look at our packages and see if we have psych. When you do this, it'll probably look like that, and you can type in psych, and I see I already have it. If you search, I almost said Google. If you search and you see that there is no psych package here, that's when you're going to use this install code. If you see that there's a psych package already there, you do not need to install it because you already have. We've used psych before, so if you've done a lab or something, when we use this, you should already have it installed. If not, you'll just run that R code. It'll go through some ugly looking red crazy stuff down here, red crazy text down here. It might look angry. It's not. It's just downloading, and then you'll wait till all that stops. Then when we have our package installed, we need to activate it to tell R that we want to use the functions from this package. So if we don't activate a package, let's try to run this function without activating the package, it's going to get angry at us. Angry R. We needed to tell it, hey, we want to use this psych package using this library psych line. And then it'll tick it saying that, yep, we're activating it. Okay, now if we try to run it, we'll actually get something. It's not angry anymore. So let's walk through what we have going on here though. We're using this describe by function, and now you'll notice that B is capitalized. So I always recommend copying and pasting the R code right now while you're getting used to all this. You're welcome to type it out yourself, but you might have errors and things that come in when you write everything yourself. So we're using the describe by function. We want to describe this variable language score. We're going to get some descriptive statistics, but we want to get those descriptive statistics broken down by group. So we're using that same convention that we've been using before that we're familiar with now at this point, where we name the data set that we need to look for our variable in, and then we type in the variable name, right? If we just type in language score and group equals to group, without that, it's going to get angry because it says we do not know what language score is. You have to tell R to look for that variable in that CH15 data set. You have to tell it where to go. Okay, so we say look in the CH15 data set. We want you to tell us the descriptives about the language score, and we want you to break down those descriptives by that grouping variable. Again, the name that we're using here is based on what we called it there. If this variable was called the flying spaghetti monster, then we would set group equals to ch1 $ flying spaghetti monster. We didn't do that because that doesn't make sense, but you're just getting an idea here that this is coming from our data set, the names that we're using. All right, so let's walk through our group, our describe by. Here, I'll run it again. So here we see descriptive statistics broken down by each group. There's the 10-hour language program, the 20-hour language program, and the 5-hour language program. And we have our hordes of children, and those hordes are equal to 10. We have 10 children in each group. The reason why I can tell that it's 10 is we have our N, and remember N is sample size, so it's a number, right? It's a number of people in our group, and N is equal to 10 for all of the groups. Then we can see the mean. We see the mean for the 10 hours is 85.2. The mean for the 20-hour group is 91.6, and we're saying to ourselves, oh, that's bigger, right? 85 is bigger than 91. And then for the 5 hours, we have a language score of 96.6, and that's smaller. Now, so we're testing our null hypothesis here, which is that the means are equal to each other. At this point, we cannot reject the null hypothesis. And the reason is, even though we know these means are different, the reason is because these means are based on the sample. They are not based on they're not an estimate of the population means, right? So just because we know our sample means are different does not mean we are certain or fairly certain that our population means are different. That's the whole reason why we're doing these statistics, is because we have our little sample and we want to be able to generalize or have a good, an understanding of to the extent to which these findings generalize to a larger group of people, a hypothetical larger group of people. So it could be that these mean differences are just due to chance. They're just due to random variation, and we're not, if we got different groups of preschoolers, maybe we'd get a different number. So that's why we can't just use these numbers to reject our null hypothesis. We have to run our ANOVA to get a statistical inference that gives us an idea of how certain we are that these are, legit or they're due to chance, these differences. Okay, that's my little soapbox there, my little plug for inferential statistics. Now we can see the standard deviation. Remember, standard deviation is a measure of average variability. And it's 6.2 in this 10-hour groups, and then the standard deviation is actually quite a bit smaller in the 20 hours. So there's less average variation in the 20-hour group. People are more closely, more similar to each other in this 20-hour group. And then in the 5-hour group, there's a huge amount of variation, right? The standard deviation is 11.96. So a lot more within group variability for this 5 hours, not that much within group variability for the 20 hours, and then medium amount of within group variability for the 10 hours. Standard deviation is somewhat related to the concept of mean squares that we use to create our F statistic that I talked about in our other video. All of these kind of sum of squares, mean squares, standard deviation, variance, they're all kind of tapping into the same concept when you're looking under the hood and you actually look at what algebra is going on there. You guys don't need to worry about that, but they're all tapping into this concept of variance, just slightly different manifestations of variance. Okay, so now we can run the ANOVA. When we're running the ANOVA, we're using a slightly different format for our R code than we would otherwise. So here we're actually making an object, and this object is going to store our ANOVA that we run. Our analyses are being stored in this M1 object. I could, again, call this whatever I want. But we're calling it M1 because we're creative and festive. So I make my object M1. That, you always know you're making an object when you have this arrow insignia here. Then our function is AOV. That's how we run our ANOVA. And we tell it that we want to see the differences on the language scores. So we're telling it the variable here. Now you'll notice we did not use the same naming convention that we normally do, right? We didn't tell it to go find the variable in the data set with this $sign. So why didn't we do it that way? Because you can also tack on a comma for some functions like this one, and then set the data here equal to ch1 5 ds1. I suspect you would, bear with me here, I'm going to just test something. I suspect you could actually do it both ways. We're kind of going off script here. Yep, you can do it both ways. You can either stay with the regular way if you want, or you can do it with just naming the variable without the data file attached to it, and then the grouping variable, and then set the data here. In either case, you have to tell it where to find the data, because if you don't, it won't find it. It doesn't know where to go. So you can, like I said, you can do it any way you want. You can do it classic way, or you can do it the new way. But you have to tell it where to go. Okay, so we made our object, and you'll notice that we don't have any output here that tells us our findings, right? You kind of got a sneak peek up there, but just because we ran our analyses, now we don't know what our F statistic is. We don't know if it's statistically significant, or our F test. We don't know if it's statistically significant. We need to do another line of code to get our results for this when we're using this format here, this ANOVA format. So we run the summary function on that object we made that's storing our analyses. And now it gives us this nice, cute little output that gives us our results. All right, so let's break this down a little bit here. We see that our F value, our F test here, is 8.799. So that's pretty big. And We also know that it is statistically significant. How do we know that? The PR, this line or this column here in our results, is telling us the statistical significance. So it's 0.00114. That's smaller than 0.05, which is our cutoff threshold for statistical significance in the social sciences. In sociology, psychology, that's kind of the convention. So then we can, well, what does this mean? This means that there is a statistically significant difference in our group means. So at least one of our groups is different, statistically significantly different from at least one of the other groups. Importantly, we don't know which group difference, which two groups essentially, is driving these statistical significant results. It could be that the 5 hours is different from the 10 hours, the 10 hours is different from the 20 hours, or the 5 hours is different from the 20 hours, and maybe the 10 hours and the 20 hours are the same. We don't know from just these results. We'll have to do some post hoc analyses after to figure this out, but we'll get to that later. So we got our results. How do we report them? We report them using this format. So we tell, we're reporting our F statistics. So we set, F, then we do parentheses, degrees of freedom for the group. And that is displayed to us right there. Your book tells you how they got these degrees of freedom. This is essentially the number of groups minus 1. Don't need to worry too much about that, just in case you're curious where that came from. Then we have the degrees of freedom for the residuals, and that is the overall sample size, which is 30, minus the number of groups, which is 3. Okay, cool. So then we report our F test here. And remember, we usually, with almost everything, when in doubt, we round to the second decimal. Sometimes there's some leeway with the p-value. Sometimes when you're writing a report, they want to know the p-value down to maybe the exact p-value. But when in doubt, 2 decimals. So we round up because 0.79, 9 is above 5 in that second decimal place there, so we'll just go up to 0.08. And then we can say p is less than 0.01. Or actually 0.011. Is that right? No, it's not. It's close though. Okay, so that's how we would report that. And what this means is we reject the null hypothesis that our means are all the same. And we say there is a good chance that our research hypothesis that the group means have a statistically significant difference, there's a good chance that that's correct. Okay, so something you have likely noticed is that statistical significance does not necessarily tell you how big or how meaningful our results are. So just because you got a really, really, really low p-value does not mean that you got a really, really, really big effect. There's a lot of reasons why that can happen. The p-value is based on partially on the sample size. So if you had a huge sample size, let's say you tested 10,000 people, it's a really, really large sample size. You're probably going to get a really small p-value because you have a good guess that whatever differences you found were not due to chance because your sample size is so large. You could have a really small p-value for a very also very small difference in means that maybe you wouldn't even really care about that much. So because there's the statistical significance is not the same as the how large the effect is, then we need to look at this effect size calculation. Right, so this is kind of giving us a sense of if our results are meaningful, are they big? And if we were, let's say for this language program, if we were testing these different language programs, we'd likely want to know if the increase in language scores is quite large because this might say, yeah, okay, this language program costs maybe some money, but we see a huge improvement in people's test scores, so it's worth it. That's the kind of question the effect size calculation allows us to answer. So for the ANOVA, we calculate the effect size, which is called eta squared. I also think of it as squiggly n squared because eta is represented by like a squiggly looking n thing. We calculate it by looking at the sum of squares between divided by the sum of squares between plus the sum of squares residual. And you may be thinking to yourself, oh, the sum of squares sounds kind of like the mean sum of squares. And they are similar. They actually are related. If you take, here's where we see our sum of squares. This is where we get this information from. If you take the sum of squares and you divide it by the degrees of freedom, guess what? You get your mean sum of squares. Same here. Take your sum of squares there, divide it by the degrees of freedom, and you get your mean sum of squares for the residual. And you divide that by that, and you'll get your F value. But you don't need to worry about all that because R did it for you. What we do need to worry about is how to calculate the effect size. So we take the sum of squares between by looking down here at our results. We see sum of squares, and between means that we're looking at the group sum of squares. So it's between sum of squares between groups. So I already did it up here, but to calculate the effect size, we have the sum of squares between, then we divide it by the sum of squares between plus the sum of squares of the residuals. The residuals are really just kind of the error. It's unexplained variance. You don't need to know, you don't need to worry about that either at this point. Okay, so you run it, and we get a really big fraction here, a really big number. And I know that this is a big number, so we get 0.39, and we'll round down because the next number is 4. So 0.39 is a big number, and I know this because your book tells you sort of these benchmarks for effect sizes for eta squared. Eta squared or squiggly n squared. These are just conventions for just kind of generally agreed upon effect sizes. So a small effect size would be about 0.01, medium effect size is up to 0.06, and a large effect size is 0.14 and above. And so what we see here is we're way above this 0.14. That means we have a really big effect size. And how we would interpret this is that the language program that we have has a really big effect on language scores. So it's a helpful program. Now, what we still don't know is that is which of the group comparisons are driving this statistical significant result. We still haven't gotten to that point yet. So we don't know if it's the 5 hours making a difference or the 10 hours making a difference or 20 hours compared to all these different ones making a difference. We have to compare the groups individually later. So first, before we actually run our Tukey HSD test, which will tell us the specific differences between our groups, we can get a general sense of how our groups look by running this box plot. So for this line of code, box plot is the argument. Now we're using the same convention that we had for the ANOVA code, where we just name the variable we're interested in, throw in a tilde, make sure it's a tilde and not a comma or something like that, and then we tell it the grouping variable. Next, we put in a comma, and we set the data equal to our data object here. Now, we can tack on the same arguments to add the title for the main title, and then the x-axis and then the y-axis. So for our main title, we'll just call it language scores. We could be a little more creative or a little more, in depth than that, but for now we'll leave it at language scores. The x-axis we're going to call groups, and then the y-axis we're going to call scores. So now we can run this code, and bada bing, bada boom, you got yourself a graph. If for some reason that doesn't just automatically pull itself up, then you click on plots and it'll show you a graph. Now if we're copying this, you can copy to clipboard, copy plot, and then paste it into your file. So here we see that kind of what we saw already in our descriptive statistics, but we can see that the 5-hour group has a really big range here. And the mean is lower than the other groups. That black line is the mean. Then we have, and the whiskers is kind of showing the range. Then we have the 20 hours and the 10 hours, and these are not that different from each other. They're a little different, but they're not really that different. And for this 10 hours, we also see a little outlier. So maybe this is just some protege language genius kid who would have scored 100 no matter what group they were in. Okay, so that's just giving us a sense of what our data looks like. Now we can run our post hoc test to see what the differences are, where these statistical significant results from our F-test are coming from. So this is called the Tukey Honestly Significant Difference Test, which makes me want to eat turkey. So it's telling us where these statistical significant differences are coming from. It'll tell us the mean group differences, whether or not they're statistically significant from each combination. So here we use our function. It's Tukey HSD, and then we put that ANOVA object in the parentheses after the function. So that's why we made it an object instead of so that we could do other functions on our analyses to get different information, essentially. So here we see, let's unpack these results a little bit. Here we see the comparisons between the different groups. The 20-hour group compared to the 10-hour group, there's a mean difference of 6.4. And we can tell that the mean difference between those groups is not statistically significant. So we can't really be certain that that 6.4 is real or if it's due to chance. Here it's saying, it could be just due to chance. We're not confident that this 6.4 difference would hold up. So we see the p-value over here in that PADJ column. It's 0.19. That's above 0.05. It's larger than 0.05. So we would say this is not a statistically significant difference between those groups. Based on our results, we can't say that these groups are actually perform better than each other on the language scores. Now when we compare the 5-hour group to the 10-hour group, we see the mean difference is negative 8.6. And it's negative because it's putting the 5 hours before the 10 hours, and the 10-hour folks are scoring higher. Now, what we notice here is that our p-value is quite close to 0.05. 0.05 is the cutoff where if the p-value is less than 0.05, then we would say, yes, that's a statistically significant difference. This is just slightly above 0.05. And really, it's not, if it's just above 0.05, it's not really there's no magic reason why 0.05 is it's not a magic number or anything. This is marginally statistically significant because it's close. So now we can look at this, the difference between the 5 hours and the 20 hours. And here there is a mean score difference of 15. Again, it's negative because the 5 hours is before the 20 hours. And you'll notice if you added that 8.6 plus the 6.4, you'd get 15. Okay, so when we're comparing the 5-hour group to the 20-hour group, we finally do get our statistically significant difference. So here this is much lower than 0.05. So we can be pretty sure that the kids in the 5-hour group had a lower mean score on their language scores than the kids in the 20-hour group, and we're pretty certain that that effect is not due to chance. So that is all the code that you need, basically, to run an ANOVA and to analyze these results. So basically what we would have here is a statistically significant F-test, which you would report as follows. And we would interpret this as there's a statistically significant difference between the kids in the 5-hour group from the kids in the 20-hour group. Marginally statistically significant between the 5 hours and the 10 hours, and then no statistically significant difference between the 10 hours and the 20 hours. These are functionally equivalent to each other. So that's your R code. Let me know if you have any questions, of course, if any errors come up, anything like that. I recommend, just copying and pasting over into your new file when you're doing this so that you hopefully don't run into too many errors. But otherwise, good luck.